So, welcome everybody to lecture 13 of this course on models of quantum computation. So we are finishing the model of quantum computation with magic states today. Here's the outline. So we want to talk about why contextuality is a precondition for quantum speedup, at least in odd dimension, and why the case of d equals 2 is an odd case, like all the other even dimensions. So there's two papers that I would like to recommend for you. The first paper is the original paper on the subject on contextuality in magic state quantum computation. It is in fact a Nature paper published in Nature, and it's by Mark Howard and company from the University of Waterloo. The other paper is by Nicolas Delfos, and yeah, so it's along the same lines with a simplified presentation of certain arguments, and we will reproduce arguments from that paper today. Good. Contextuality is a precondition for speedup. So here's something that we learned in lecture 11, that's theorem 1. Quantum computation with magic states can have a quantum speedup only if the Wigner function of the initial magic state has negativity in it. So today we'll talk about a similar theorem where Wigner function negativity is replaced by contextuality. So it says, quantum computation with magic states can have a quantum speedup only if the initial magic state is contextual. Yeah, okay, that's what we're going to talk about for most of the class. Yeah, so first we have to deal with the question, when is a quantum state contextual? So we can first a comment. So that's the bullet here. So for this question to make sense, we require that ontic states new with value assignments exist. That is, when the setting is not state-independent contextual. Yeah, if we have state-independent contextuality, then we do not even have consistent value assignments. Remember Mermin square and star. Yeah, so when that happens, we cannot talk about state-dependent contextuality. For state-dependent contextuality, we require consistent value assignments to exist. Okay, so now when they exist, we can have the following definition. A quantum state ρ is contextual if no probability function from the set of ontic states exists that can reproduce the measurement statistics for all available observables. Yeah? So we can measure a bunch of observables, and then the goal for this model is, for the hidden variable model, is to reproduce the measurement statistics for these observables. And if that fails for all probability functions P, then the state in question is contextual. If, however, we can reproduce all the measurement statistics on a given quantum state, then we call that state non-contextual. So one point remains to be discussed, and that is what does it mean here, available observables? I mean, it looks, yeah. Okay, and for that we refer to our computational setting as an example. So an example of that could be when we can measure all while operators and nothing else. So that's exactly our computational setting. So we do not need to be able to measure all observables, be able to measure in all bases. Yeah, we can restrict the sets of observables we can measure according to the setting we are interested in. Yeah. So maybe let's illustrate that in an example. So an odd dimension, yeah, our scenario of quantum computation with magic states is a scenario where we can measure all the while operators, and we have the corresponding value assignments. So value assignments do exist. We have one value assignment for each point in phase space. So the phase space of the model is our state space. Okay, so value assignments exist, hence on-tick state exists, hence we can ask the question, when is a quantum state contextual? Okay, and we will do that now. Okay, so but let's go back to theorem number 2. So maybe we quickly go back to it, what it said. So quantum computation with magic states can have a quantum speedup only if the initial magic state is contextual. What we are going to prove here is the contrapositive. So when a quantum state rho, the magic states, is described by a non-contextual hidden variable model, that is, it is not contextual, then efficient classical simulability follows. Yeah, so it's completely analogous proof as we did for positive Wigner functions. In fact, we will make use of that earlier proof. So what we are really going to show here is that the existence of a hidden variable model for the magic states that can describe all measurements of while operators, the existence of such a model is equivalent to having a positive Wigner function. Yeah, so that's what we will prove today. And then we combine this result with the earlier result that we had on Wigner functions, namely that positive Wigner functions imply efficient classical simulability, to show the same for the existence the existence of a hidden variable model. So this part here on the left, the yellow and the blue bubble, their relation is what concerns us today. Yeah, and in this bijection, we have a forward direction and a backward direction. The backward direction is easy, and the forward direction is what we need for our proof. And so even if strictly speaking, the backward direction we do not need for our proof, we will nonetheless present it here because it gives you an idea how positive Wigner functions and hidden variable models are related. So in fact, that is what we begin with. And then the harder case of the forward direction, which is also what we really want to talk about here, comes later. Okay, so let's get started. Yeah, so what we're showing now is that the positive Wigner function implies that rho is non-contextual. And basically, we have already done that in lecture 11. So remember when we talked about measurement outcomes and Wigner functions. So what you see here is the expectation value of a while operator W of A. Yeah, so A is the label of the operator. Yeah, given a state rho. Okay, so now we want to write this thing in terms of the Wigner function of that state. Yeah, and so after some calculation, we arrived at this expression. So that expectation value is a sum over all points in phase space of the Wigner function at that particular point in phase space and a value for that observable, yeah, given we are in that point in phase space. And then we also observed that this conditional value that was assigned to a point in phase space is an extremal value that these observables can have. So yeah, so that's illustrated in this plot. Yeah, so here you have these red dots are the eigenvalues of the respective observable for the case where the dimension is 3, just a special case here. Yeah, and so then the expectation values that are possible, they lie in the span of these 3 points, that is in this shaded triangle. Yeah, and these assignments here, they are the extremal points of this region, so they are deterministic values. So you can say, if you are in a state V, that is the value you get with certainty. These are deterministic values exactly as required in a hidden variable model, non-contextual hidden variable model. Okay, good. So now what does this all mean? So it means that if our Wigner function is positive, then we can, yeah, normalization condition is always satisfied for the Wigner function. So Wigner function summed over all points in phase space is 1. Yeah, discussed this maybe last time. Okay, so then if the Wigner function is positive, we can regard it as a probability distribution over phase space. Yeah, so the Wigner function becomes a probability when it is positive. Okay, so here's a probability, and then this is the conditional value. So if you are in a state V that occurs with the corresponding probability, the conditional value is that thing. Okay, so now this value here, this value assignment, that becomes the value assignment of our hidden variable model if our ontic state is V. Maybe I should have started over here on the left rather. So our phase space is now the set. What's the phase space for the Wigner function now becomes the set of ontic states for our hidden variable model. So every point in phase space is an ontic state of that hidden variable model. Yeah, so the only other thing that we need after we have identified the ontic states is what the value assignments are for these states. And the value assignments are given by these expressions. So maybe let me briefly talk about notation here. So we see the dot. So this dot stands for any element A that labels the Heisenberg-Weil operators. Okay, so you can plug that in here, and that will also then be the value assignment for that observable A in the state V. Okay, so from the Wigner function formalism, if the Wigner function is positive, which gives you the probability distribution, so if the Wigner function is positive, you get everything that you need for your hidden variable model. Yeah, so that implies what we wanted to show. Yeah, if we have a non-negative Wigner function, we have a non-contextual hidden variable model describing the measurement statistics for um, all the density matrices. For which the Wigner function is positive. Okay, good. Yeah, so that was the forward direction. So now about the backward direction. Yeah, is it true that whenever we have a hidden variable model for our state rho, that it also implies a positive Wigner function? And yeah, and so what is this question really about? What could be in the way of that? So what could be in the way of that is that we have, in addition to, so here is the phase space. Every point in phase space gives us a proper ontic state with a consistent value assignment. But what could be in the way is that you have additional ontic states that also have consistent value assignments, which have, however, nothing to do with Wigner functions. And so if you had a hidden variable model and a state that had support on these extra ontic states, well, then you could not map it, not necessarily map it to a positive Wigner function, because simply you would have to figure out how to map that stuff. Okay, and so that would be the spoiler. If you find additional states, that would spoil the equivalence. And so the question is, are there other ontic states other than the points in phase space that you already have? And the answer is there are not. At least if you have more than one quantum system, then there are not. Okay? And that is what we want to that's what we want to prove now. Good. And so the way we are going to prove it is that we make an observation about the structure of the value assignments. Namely, we observe that they are characters of our group here. Yeah, so ZD to the n tensor ZD to the n, that is the group of translations on this phase space. And all our value assignments are characters of that group. That's the observation we make, and we will use it shortly. Okay, so first we have to show that, and for that we introduce a little bit of extra notation. So in the following, we are switching from multiplicative to additive notation. So multiplicative notation is this here. So this is our value assignment lambda for a state, ontic state V of the observable labeled by A, and that value is omega, our dth root of unity, raised to the power of this symplectic inner product of the observable you care about, A, and uh, your point V in phase space. So this is the value assignment in multiplicative notation. So we write this as omega to the power SV of A. So this new notation replaces the value assignment lambda by this value assignment s. And s is now an integer in ZD. Yeah, 0, 1, 2, 3, 4, 5, up to d minus 1. Yeah, good. Okay, so back to multiplicative notation. So we have the following consistency relation for these value assignments. I mean, what we physically need to require is that this thing holds here. Lambda of A plus B is lambda of A times lambda of B. I mean, physically motivated is to have this constraint whenever A and B commute. Yeah. So we discussed this before. So whenever these observables are measurable, then it's meaningful to enforce this constraint. Okay, but we observe, since we have a character up here, then this condition holds regardless of whether A and B commute or not. So so these lambda assignments, they satisfy a stronger condition than what we would straightforwardly see from or require from the viewpoint of physics. Let's do this now in additive notation. Same thing in additive notation. And this additive notation will pay off later. That's why we are making the switch here. Okay, same argument in additive notation. So just kind of from examining this assignment, and since this symplectic linear product is bilinear in both factors, we have that, yeah, so this thing translates to S of A plus B, yeah, is S of A plus S of B mod D. So the content is the same as above, but we have now changed the notation in preparation for what's coming up. Okay, and this is supposed to hold for all points in phase space. So you have this label of phase space point down here. This relation has to hold for all of those. Yeah, it has to hold for all A and B, regardless of whether they commute or not. So this is what holds for all these value assignments. Okay, and that property makes these assignments characters of that group of translations on phase space. So the number of characters is an abelian group, and so the number of characters is exactly the number of group elements, and so there's d to the 2n of them. And they are in a one-to-one correspondence with the elements of phase space. Yeah? So for every element in phase space, you get a corresponding assignment. Okay. So what have we shown? We have shown that our non-contextual hidden variable model value assignments, they correspond to the characters. So they are characters and they cover all the characters there are. Good. Okay. So now let's continue. Oh, easier said than done. Let's see. No, I don't want to add text. I just want to go to the next slide. So, okay. So now what we have to show, so far everything that comes from a Wigner function is a character. So now we want to show that for any odd dimension d larger than 3 and any number of particles n that is larger or equal to 2, so the case of n equals 1 is excluded here, the value assignments, lambda nu in multiplicative notation, s nu in additive notation, are characters of V. Yeah, so there is, yeah, so for the Wigner function value assignments, we have already seen it. And now we are going to show if that condition holds, then any possible value assignment must actually be a character. Okay, good. So that we now prove. Okay, and the proof begins by considering a canonical basis of our group here, and or phase space if you like. And so that would have, say, the x part here, particle 1, particle 2, particle n, and then the z part. Yeah, so that would represent our basis. And so we have that the symplectic inner product of vector ei and fi to give us 1, yeah, corresponding to the commutation of x and z, which is omega. Gives you, under exchange, you get a factor omega to the power 1, and that 1 is what you see here. Okay, so that's the first property. And now we consider planes. And a plane, each of the planes we consider here is associated with a certain particle I. And I goes from 1 to n. And it is generated by EI and FI. So EI is for the x part of the observable on particle A, and FI is for the z part of that observable. And such planes, corresponding to different particles, they are orthogonal. Yeah, so remember, orthogonality represents commutation in observables that sit on different particles. They trivially commute. Okay, so we have orthogonality whenever the particle labels I and j are different. Yeah. And pi, which is a plane, stands here for all the possible linear combinations of ei and fi. Yeah, so you have coefficients in ZD in front. And this commutativity holds whatever these coefficients are. So we already know something, and that is, so the basic starting point, that we have linearity of these value assignments when the arguments here u and v, when they commute. Okay, so that we can already use, but we wanted to prove something stronger, namely we have the linearity always. Okay, because of the orthogonality of planes, we observe the following. So let's expand that vector u. So it's a linear combination of all the ei's and all the fi's. Okay, and for the value assignment s of u, s of this thing, we can already write it as a sum of over the particles, going from 1 to n, and sum of value assignments. And the reason that this holds is that the commutativity condition is trivially satisfied when these vectors correspond to different particles. Yeah. Good. Okay, so we arrived there. And so now what remains for us to show is that these sums here, or these, I mean, we have these summons, we have n summons, and yeah, they still have these arguments consisting of x part and z parts of the observable living at site I. Okay, so now all we want to show, what remains to show, is that these also split up. Yeah, so we have linearity also in this argument. That remains to show. And that is what we show now. Okay, so still before the calculation starts, one step of preparation. So to show this, so we now look at two vectors that have support only on particle number I. So the observable u has only uh, only invokes the vector ei, so that's the x part, and the vector v only invokes dear. This is supposed to be an fi. I apologize for that typo. So v is here for the z part, therefore the vector f. And yeah, so but the important point is that u lives on particle I and v lives on particle I. And now, based on those coefficients alpha and beta, we introduce another vector u prime and another vector v prime, and they are defined with the same coefficients that we already had. Um, so, but yeah, so the beta occurs now for u prime in the x part, aj, and alpha now occurs in v prime with the vector fj. Okay, so what matters about these two vectors apart from the choice of coefficients alpha and beta is that they live solely on particle j. Particle j is another particle than particle I. So by the way, here is where n larger or equal to 2 comes in, because we are starting with some particle I and we need another particle j. So that means at least two particles must be present. Okay, so now given u and v, for this choice of u prime and v prime, we obtain that uh, the symplectic inner product between u and v and between u prime and v prime agree. That's an easy calculation. Okay, so based on that, we now have the following thing. So now we are looking at the symplectic inner product between u plus or minus v prime and v plus or minus u prime. And we find, okay, so this gives us four terms. We just this bilinear expression. So we are getting four terms. Yeah, so then two of the terms have only e parts and two of the terms have only v parts. So they are individually zero and drop out. And then we have two parts remaining. One symplectic inner product between u and v and one between u prime and v prime. Yeah, so going from here to here, we have exchanged the order of arguments, so that brought down a factor of -1. And then we are using that property up here and find that the two contributions cancel each other out. So that is a property that we will subsequently use, and so we give it an equation number. So next step, so there's, I think this is now really the last step before the calculation starts. Okay, so now we write the sum u plus v in a certain way. So we write it as two terms. So we write u plus v as the sum of two terms. And you see that there is this dummy part u prime plus v prime that cancels out here versus here. So we have just added a 0 and then put brackets somehow. Okay, but the interesting thing about this step is that we have now two vectors that are pairwise orthogonal, this and that, which we will use later. Okay, so let's prove it that these are really orthogonal. So now we had, again, the symplectic inner product is bilinear, so we have, I mean, four terms here, so it gives us the sum of 16, but most of them are 0 because either they compare u and u, I mean u and u or u prime, I mean, yeah, same type, or they, yeah, v and v prime, yeah. So most of these combinations drop out, and all the individually non-vanishing contributions are here. So, so they are. So symplectic inner product between U and V. So this comes from here and here. And then we have next, we have the symplectic inner product of V and U. So that's over here. And then with minus signs, we have U prime with V prime, minus sign coming from here, and V prime, U prime also with the minus sign coming from here. So now we recall that the symplectic inner product is antisymmetric, so we can exchange the order, and then we see that those two, the first two, cancel each other out, and the third and the fourth likewise cancel each other out. So yeah, so that symplectic inner product is 0. So these two are indeed orthogonal. Yeah, good. So we give this also an equation number because we'll need it momentarily. So now we're using, or we are about to use property 2. So, but first, yeah, so this is what we care about, the value assignment for this vector. So which is by what we had. So we're just applying the value assignment to this argument. So nothing much happening yet. Okay, so the next step is we use property 2 because these vectors are orthogonal. That is, yeah. Good. So let's do that. Yeah. So this is the sum of these value assignments. Okay. And so now next step is we are putting our brackets conveniently. So we are bunching up U with V prime, and we are bunching up V with U prime. And we do the same thing on the other side. We just have the minuses. Okay, so that's something that we can certainly do. Addition is associative. Good. Okay, next step, we are applying our equation 1. So I have this, in case you forgot, I have redrawn it up here. So that's something we showed earlier, that the symplectic inner product, say U plus V prime and V plus U prime, that they are 0. Yeah, and so you see this precisely. Oops, no, let's not go there yet. Yeah. So yeah, so this and this commutes, and so we can pull it apart as far as the value assignment is concerned. So the value assignment of the sum equals the sum of the value assignments. Okay. And yeah, similar thing happens over here. Good. So second last step. So now we look at these individual for value assignments. So again, so U and V prime are orthogonal because U lives exclusively on particle I and V prime lives exclusively on particle J. Yeah? So they are orthogonal. So we can replace S of U plus V prime by S of U plus S of V prime, and we do the same with the other 3 terms. So in all, 4 terms become 8 terms, and you have them here. Okay, but now you see various terms occurring multiple times. In fact, every term occurs twice. And some of those occur twice with the same sign, and others occur with opposite signs. And so the ones with the opposite signs cancel out, and the ones with the same sign amplify. Okay, and then this factor of 2 cancels the 1/2 outside. So overall, we arrive at this. Yeah. So we arrive at S of U plus S of V at the end of the calculation. And now we have to remember where we started from. Started with this, S of U plus V. So this is precisely the linearity we wanted to show. So we have shown that indeed every value assignment, every consistent value assignment is a character as long as we have 2 or more particles. So recall that this proof wouldn't work with just a single particle because we needed I and j to do the proof. Okay, so that's the end of the proof in the technical sense, but we still need to kind of remember what it was that we wanted to show and where this result helps us. Okay, and that is shown here on this slide. So we have shown the following things. So we have shown that the hidden variable value assignments we are getting from phase space, they are all characters. So this is one thing that we showed. And the other thing that we showed is, oh, excuse me, sorry, I said that wrong. So the, let me back up here. Uh, so everything that comes from the Wigner function, all those value assignments, they are characters, and there are exactly as many characters as there are points in phase space, and so every point in phase space corresponds to a character. Yeah, so there's 2 to the n characters, 2 to the n points in phase space, 2 to d to the 2n points in phase space, and there's a one-to-one mapping between them. Okay, so that's the first thing we showed. Second thing we showed is that every value assignment, regardless of whether it comes from a Wigner function or from wherever else, is a character. And so now, since all the characters there are already taken up by the Wigner function, there can be no other characters, hence there can be no other value assignments, hence there can be no other ontic states. Yeah. Okay. And so therefore, if a Wigner function, excuse me, if a hidden variable model exists for our state row, then it yields a Wigner function with non-negative Wigner function. Good. So that is now what we wanted to show. Non-contextual hidden variable model for the state row implies non-negative Wigner function. Good. Okay. So, and this is how we use it to prove our final theorem. So if we have a non-contextual hidden variable model available, we've just shown that it leads to a non-negative Wigner function. And then we already know from lecture 11 that this implies efficient classical simulation of our magic state quantum computation. Okay, so that's the proof of theorem 2, and that ends this part of the lecture. So what remains? One comment before we end. Okay, so now we have shown structurally the same results for Wigner function, negativity, and contextuality, and namely, excuse me, namely that there are preconditions for speedup. And these two properties are not alone in the list of usual suspects for which you can show such theorems. So you can also show a theorem of this kind for entanglement and one for superposition and interference. So all these are preconditions for quantum speedup. Yeah, so at this point, it becomes interesting to ask which quantum property is sufficient for quantum speedup. Not necessary, but sufficient. Okay, there's considerably less work on that question. Just let me say that. Okay, so now the other part, and this is the shorter part in this lecture, and so we are now done with our main theorem, but it had the restriction that it applied only to odd Hilbert space dimension. So now let's turn for comparison to the simplest even dimension, which is d equals 2, which is the qubit case. And the qubit case is odd. I mean, 2 is of course even, but d equals 2 as a case is rather odd. And the reason that this is so is the presence of these Merman's creatures, yeah, Merman's square and Merman's star. So they make life complicated in even dimensions. And let us see why this is so. Okay, so here is the statement that we want to prove. I mean, at least in a somewhat constrained setting. Yeah, so there's more general proofs around, but I just want to give you the gist of it, and you can look up the generalizations later if you like. So here's the statement. So there is no Wigner function on n equals 2 or larger than 2 qubits, yeah, n or more qubit, 2 or more qubits. So there's no Wigner functions on them that can preserve positivity under all Pauli measurements. Okay, so let's just look at that. Let's make our scenario as simple as possible. Let's consider a 2-qubit Wigner function. And so we're looking at the phase point operators. The phase point operator at the origin is like this. So it's this, as we had it before, the sum of all while operators. That's the Pauli operators here in the case of d equals 2. Okay, and we might want to work with different phase conventions here. So not our, yeah. So remember in the odd dimensional case, we had a standard phase convention that doesn't exist in even dimension. So we're not fixing the phase convention for these while operators. So just we are using a phase convention that is such that all these operators have eigenvalues +1, -1. Yeah, so that gives us a 1 bit of freedom for every A. Good. Okay, so this is our phase point operator. So we admit this generality in the phase convention, but what is special about this definition, oops, like we had it for Q-dits, is that these while operators, they are all weighted equally. So there's none who have a large weight and others have a small weight. No, they have uniform weight. So that in that regard, we are special. Good. Okay, so that's the expression for the phase point operator at the origin that we are considering. And then, as we had it before, the phase point operators at other points in phase space, they are given by conjugation of phase point operator at the origin under while operator with label A. Excuse me, while operator with label U. Yeah. Label U here, label U here. Conjugation of the phase point operator at the origin. Yeah. Okay, so this is the definition of the Wigner function we are working with. Yeah, good. And now we're asking for a Wigner function like that. Whatever the phase conventions are, can the Pauli measurements preserve positivity always? And that's not going to be the case. We want to show that, and we take a slight detour, and we are asking about the Wigner function of a stabilizer state. So is it always positive? And we will show that this is not the case. So yeah, so that's not the proof why this is not the case. So because of Mermin's square, we can always, what is going on here? We can always find a triple of commuting operators, W of A, W of B, and W of A plus B, such that W of A plus B is minus the product of W of A, W of B. I mean, the ideal situation would be that this minus sign never occurs. But because of Mermin square, yeah, I remember the observables occurred here. Yeah, there was always one context where the product was minus the identity. And that's just what you see here. And yeah, so you can shuffle that minus sign around by changing your phase conventions for the W's, but you cannot eliminate it. It was precisely the non-existence of a hidden variable value assignment. Okay, so you can shuffle around the minus in the square, but you can never eliminate it. Okay, so we are looking at a context where it arises. Okay, and now we consider the stabilizer state with the satisfying these two constraints that would fully define it. So W of A of psi is minus psi, and W of B applied to psi is also minus psi. Okay, and then the consequence of that is that W of A plus B applied to psi is minus the product of the two, W of A and W of B applied to psi, and then using the stabilizer relations, it gives us two additional minus signs to cancel. So that minus sign survives. So W of A plus B applied to psi is also minus psi. Yeah, and then because of these properties, the density matrix psi, capital Psi, is 1/4, and then the sum of these four while operators, the identity minus W of A, minus W of B, and minus W of A plus B. You can check that that state satisfies all these stabilizer relations. Yep. Okay, and now we ask, given that state, what is the Wigner function of it at the origin? Yeah, so in other words, what is trace of that state, that density matrix with a phase point operator A0? Okay, so let's just use the expansions we have. So there's a bunch of prefactors here that don't matter very much. Then we have yeah, the four the for while or Pauli operators in the expansion of the state, and then we have the sum of all while or Pauli operators in the expansion of the phase point operator. Okay, sorry, I forgot the trace symbol here. Now we have a trace of products of while operators. So everything here in this first term will find a partner here and square with it to the identity, and that gives a contribution under the trace. Yeah. So we have four contributions for the trace from this one, from that one, so on and so forth. So here in the first term, the while operators, or just Pauli operators for qubits, occur with different signs. Over here, they do not. They all are with sign plus. And so these signs survive. So every identity in the four-dimensional Hilbert space has trace 4, so that's where this factor comes from. So from the identity, you get 1 here from this term, finding its W of A in here. Together, they give you a trace of -1 times 4, minus coming from here, minus coming from here, minus coming from here. And so you see, that's the sum of positive and negative terms, and the negative terms dominate. Yeah, so you have a sum of -2 from these four terms. And so overall, this gives you a negative value for the Wigner function evaluated of that state, evaluated at the origin. Okay. So that's not something that we want to see. So we have a stabilizer state whose Wigner function attains a negative value. Okay, so now let's see what this means for our original question. So we observe that since this is a stabilizer state, that we can obtain it by repeated Pauli measurements, namely the measurements of the generators of the stabilizers of that state. So that would be minus W of A and minus W of B. Yeah, so we can obtain that state by starting in the completely mixed state and then performing these Pauli measurements. That would lead us to that state. So now the Wigner function of the completely mixed state is positive. So that's something it's also easy to show. It's a completely flat distribution according to the Wigner functions we have defined. Yeah, so that completely flat is in particular positive. And we end up in a Wigner function that is not always positive, or at least non-zero. I mean, positive or, excuse me, it's not always non-negative. It has negativity in it. Yeah, so that's where we end up, starting from a positive Wigner function. And all we do is Pauli measurements. What was that? All we do is Pauli measurements. And so those Pauli measurements are evidently not positivity preserving. And so that's the upshot. For n larger than 2 or 2 qubits, the Pauli measurement cannot be preserving the Wigner function positivity. Okay, good. So that's also a difference from the odd dimensional case. And it's an important distinction because we needed that property in the odd dimensional case to prove our classical simulation algorithm. Yeah. Okay, so we see here the first example where the even dimensional case differs in an essential way, in a crucial way, from the odd dimensional case. So that was positivity preservation on the Pauli measurement, which fails. Covariance on the Clifford gates also fails, and I'm not doing it here, so please wait for that. It will occur in homework assignment number 5. So this is it. For further study, I mean, this is not the end of research on the qubit case. So it turns out that you can recover essentially all features of the qubit case in the qubit case, or multi-qubit case in the multi-qubit case, if we turn to larger phase spaces. That is, we have now phase spaces that have more than 2 to the 2n points. However, the flip side of this, now you have more points in phase space than the dimension of operators in your Hilbert space. And so the Wigner or those quasi-probability distributions or probability distributions then become non-unique. That is, for one density operator, unlike in the odd dimensional case, you can associate various probability distributions or quasi-probability distributions with them. Okay, so that's the difference that remains, but you can restore positivity preservation on the Pauli measurements, and you can restore Wigner function covariance. Okay, but that is for further study. I just wanted to mention that there is quite a bit of work on that, but maybe it goes beyond the scope of this lecture. Okay, so here's the summary. So we have talked about the scheme of quantum computation with magic states. And I talked a little bit about fault tolerance here, or in fact, I devoted a whole lecture to fault tolerance in this model. And so this model, if you are interested in the practicalities of quantum computing, this model is a leading candidate for fault-tolerant quantum computation. And remember, the reason was that the hardest gate to do fault-tolerant in a fault-tolerant fashion is the non-Clifford gate that you need in the universal set. And quantum computation with magic states allows you to get that gate in a clever way. Fault-tolerant version of that gate in a clever way by magic state distillation. So that is much more robust and efficient if you would do it in a straightforward transversal fashion. Okay, that was a practical side, and here from our resource perspective, we have identified contextuality and Wigner function negativity as preconditions for quantum speedup. So this is it. This is the end of the discussion of quantum computation with magic states. Next time we discuss, or we begin to discuss, measurement-based quantum computation. So all for today. Thank you very much for your attention.